Good afternoon, everybody. Since this talk is about reflection, I will of course start by talking about command line option parsing. I'm sure everyone loves writing code like this. Our application has 4 possible command line options. We iterate through all the arguments, looking for each possible option and processing it. This is tedious and error-prone. If we change any of the options, code needs to be updated in multiple places. And this code doesn't do any error checking. If we had just the basic error checking, enough to avoid a crash if the user types in garbage, it becomes even more tedious. But what if we could ditch all the repetitive boilerplate? Just define a struct that holds the values of all the options, and have the code automatically fill in the values of that struct from the command line arguments. That's it. No writing out the code for individual options. No code for parsing individual options. Just some generic code that does it all as if by magic. That's what reflection can do for you. Keep this example in mind as we go through the presentation. I'll show you the magic behind the parse options function later on. Welcome to my presentation about C++ reflection, where I will explain what reflection is, go over the proposal that is working its way through the standards committee, and give some examples of how reflection can be useful. I am David Olsen, the lead engineer on the HPC C++ compiler team at NVIDIA, where I help keep our compiler, NVC++, running smoothly on many of the largest supercomputers in the world. I was the driving force behind the NVC++ feature of running standard parallel algorithms on GPUs, and I am supporting NVIDIA's efforts to run upcoming standard features such as linear algebra and P2300 senders on GPUs. Before I overwhelm you with all the code examples and proposal details, I should spend some time reflecting on what reflection is. Reflection comes in 2 parts, introspection and injection. We'll cover introspection first. This is probably what comes to mind first when you think of the word reflection in a programming context. Reflection is when a program looks at itself and observes its structure and how it is put together. In other words, the program can ask questions about itself, such as, what kind of type is this? Or what are the public data members of this class? Or where are the buffer overflow bugs in this code? Just kidding on the last one. The program looking at itself is an important part of the definition. A program asking questions about another program is a static analysis tool, not reflection. Given that it is known as a reflection, you would think that a mirror is a good analogy. But no, a mirror only shows the surface of what it is reflecting. A better analogy, in my opinion, is an X-ray. An X-ray lets you see not just the surface, but the interior structure. Reflection lets a program look at how it is put together, not just at its external behavior. When asking questions about itself, the program works with reflection values, usually referred to as reflections. To get a reflection value that can be queried, there has to be some way to get from the world of code into the world of reflection. This is known as the reflection operator. In the X-ray example, the reflection operator is the X-ray machine. This is what converts a real-world object, in this case your leg, into a reflection value, namely the view of the bones inside your leg. The other side of reflection is code injection, also known as reflective metaprogramming. This is the opposite of introspection. This is lumped together under the general term reflection and differs from other kinds of metaprogramming because the results of reflection queries are used to generate code. I looked for a picture of a robot fixing itself to represent reflective metaprogramming, but I couldn't find a good one. So you'll have to settle for Escher's drawing of 2 hands drawing themselves. While introspection needs to have a reflection operator to go from the code world to the reflection world, code injection needs to do the opposite, going from the reflection world back to the code world. Every decent reflection scheme will have some way to do this, though it's usually not as simple as an operator. For reflection to be useful, there needs to be something unknown for the program to ask questions about. The unknown thing could be anything, but it is usually a type. Or reflection queries usually start with an unknown type before moving on to other kinds of unknown things. It is important that the program doesn't know what the type is, but that the compiler does know. If the code knows what the type is, there's not much point in asking questions about it. If the compiler doesn't know what the type is, then asking questions about the type won't result in any useful answers. If you have code that is working with unknown types, you usually have polymorphism of some sort. It could be compile time polymorphism, such as C++ templates, or it could be runtime polymorphism, such as object-oriented programming and class hierarchies. Programming languages that don't have any polymorphism, such as C, don't have reflection because there are no significant amounts of generic code operating on unknown types. An example of code using an unknown type at compile time is C++ templates. In the function template here at the end, the code inside the function doesn't know what type T is, but the compiler knows what type T is when the function is instantiated. Code works with a type that is unknown at runtime in dynamically typed languages or in languages that support object-oriented programming, especially in languages such as Java that have a universal base class. Compile time reflection does introspection on static types, and the code injection causes different code to be generated by the compiler. It's a good match for statically typed languages with static polymorphism or generics. Runtime reflection does introspection on the dynamic type of objects. It doesn't affect the code that the compiler generates, but instead causes different code to be executed at runtime based on the dynamic types of objects. It's a particularly good match for object-oriented languages with universal base classes. Spoiler alert, C++ will have compile time reflection. To help you understand how C++ reflection fits into the bigger picture, I want to quickly go over some other implementations of reflection. Let's look at how reflection is done in C#. While I spent a year and a half programming mostly in C#, that was some years ago. My C# skills are quite rusty. There are probably some mistakes in the following slides, but I think the overall concepts are correct. C# reflection is runtime only. It predates C# generics, so it is designed to work with C#'s universal base class model. The reflection operator is the getType method that every object has. It returns a reflection value of type that reflects the dynamic runtime type of the object. Once you have the reflection of the class type, you can navigate around with each kind of thing represented by reflection value of a different type, such as method info, constructor info, or field info. Code injection in C# is also done at runtime. You can create a new object by calling the createInstance method of reflection class activator. You can call a member function that was found via reflection by calling the invoke method of the reflection class methodInfo. You can change the value of a data member in an existing object by calling the setValue method of class fieldInfo or propertyInfo. I will use this problem as my basic reflection example several times in this talk. So let me go over the problem statement in detail now. Assume that we have been sloppy in our API design and we have created some containers with a size method and some with a length method. And we are too lazy to go fix up all the containers and make the APIs consistent. So we want to write a function that accepts any kind of object, checks if it has a method named size or length, call that method, and return the result. This is slideware, meant to show the use of reflection so the error handling is minimal. This is the C# solution to the problem. We have a method named size or length that takes a single parameter of the universal base class type object. First, we use the reflection operator, the getType method, to switch from the code world to the reflection world. Remember that getType returns the reflection of the dynamic type of the given object, not a reflection of class object. Once we have a reflection of the class type, we get that class's methods and iterate over them, looking for one named either size or length. If we find one with the right name, we call that method using C#'s code injection operation of methodInfo.invoke. Invoke returns an object, so we have to convert that to an int before returning it to the caller. And we're done. C# has code injection capabilities beyond the simple ones on the previous example. It is possible to create entirely new classes and functions at runtime. It's not easy to do. Creating function bodies requires emitting .NET bytecode, which makes the programmer do the work that compilers normally do. Here's a very simple example taken from a C# reflection tutorial. The highlighted code is emitting .NET bytecode for the function bodies. If we wrote the code directly rather than using reflection, this is what we would have. Most of the code was implementing these two simple functions at runtime. Now let's look at how C++ currently implements reflection. Hint, not really. That's why there is a proposal, which we will eventually get to, that does reflection properly. There's a tiny bit of reflection in C++ right now. Emphasis on tiny. The type ID operator can get a std type info representing a type, even for the dynamic type of an object in some cases. While this runtime information is very useful to the compiler, behind the scenes it is used to implement dynamic cast and exceptions, it's essentially useless to the end user. The only thing user code can do with a type info is get the name of the type, which might be a mangled internal name, not a user visible name. I don't know of any plans or desires to expand the functionality of type ID or type info. It is a dead end in the quest for C++ reflection. Type traits are much more useful. They allow for compile time introspection of types. There are lots of standard type traits. These are all the ones that I could find. But type traits only work on types and on properties that can be represented in the type system. You can't get the members of something, or even the parent scope of a name. You can't ask questions about functions except for things that are in the function's type or that affect template argument deduction. While type traits are extremely useful and were a good addition to the language in C++11, they are lousy at implementing reflection. Because they were never intended to be the reflection solution. Type traits and many other parts of template metaprogramming are an outgrowth of the magic of function template argument deduction that happens during overload resolution. Those rules can also be used to resolve class template partial specializations, which is what type traits are based on. One last thing in current C++ that is not reflection, but is reflection adjacent, requires expressions. A requires expression makes it very easy to ask whether or not a chunk of code is semantically valid. Requires expressions can do a couple other things, but the primary purpose is to check for code validity. It was possible to do this before with template metaprogramming, but requires expressions make it so much easier. While you can view this as a kind of introspection of the code, it is more of a surface view like a mirror, not a look inside like an X-ray. While requires expressions are not reflection, they can be used to solve our size or length problem, though the solution is not ideal. Again, we have a function named size or length that takes an argument of any type. But this time the type of the template of the parameter is a template parameter rather than a universal base class. Rather than iterating through all the member functions of T, instead we check if calling the size member function with no arguments is valid code that returns an integral type. If it is valid, then we call it and return its result. Then we do the same for length. Because we don't have the reflection with code inspection available, we can't just call whatever member function happens to meet whatever criteria we are looking for. We have to check each possible member function one at a time and call that member function directly. This scheme would break down entirely if we were looking for a member function whose name fit a certain pattern, or if we were looking for a member function with certain properties unrelated to the name. One last stop on our reflection survey, a proposal for standardizing reflection in C++ that was ultimately dropped. In the 2010s, there was a lot of work to get reflection into C++ using a compile time template metaprogramming approach. A reflection value was a nameless unique type. To figure out what kind of reflection a type represented, you would check if the type satisfied one or more of a large number of concepts. The reflection operator was the keyword reflexper. reflection queries were done via type-based template meta functions. Because everything was type-based, reflection programming was done via type alias declarations, as seen here. Getting from the reflection world back to the code world was done with more template meta functions. To get the type from the reflection of that type, use getReflectedType. If the reflection value represented a function, member function, variable with static storage duration, or a non-static data member, then getPointer could be used to get a compile time pointer to the thing. The pointer would be a regular object pointer, a function pointer, or a pointer to member, depending on what kind of thing was being reflected. This reflection effort made it as far as being published in a technical specification, or TS. But the TS was never merged into the C++ standard. In the late teens, the standards committee decided that template meta programming is just too cumbersome, and that context per functions make for a better API for reflection. So everyone shifted their efforts to other reflection strategies. A Clang fork that implements the reflection TS is still available on Compiler Explorer, so I can give you a taste of what working reflection TS code looked like. We have a function named size or length that takes an object of any type. We transfer into the reflection world with the reflexper keyword. Then get the reflection of the entire set of public member functions of the class. They are represented as a type, which is why they are stored as a type alias. Because we are working with type lists, we need a recursive class template with a partial specialization in order to iterate over the types that reflect the member functions. The unpack sequence template meta function passes the type list to our class template. Our class template checks if the current member function is named size or length. If so, use getPointer to get a pointer to the member function, and then use the pointer to member function call syntax to call that member function on the given object. From the complexity and verbosity of this code, you can understand why there was some pushback against the reflection TS and a desire for something better. That something better is reflection for C++ 26, which is currently making its way through the standards committee, where it is known by its paper number P2996. This is the meat of the talk. This is the part you should pay attention to if you are interested in C++ reflection. All the background that I have given wasn't strictly necessary, but hopefully it gives you a foundation to better understand P2996. Some past reflection proposals have suffered from being too big. The committee wasn't confident that they could get all the details correct on the first go. And once a bad feature is in a released standard, it can be very hard to fix it. So the authors of the current proposal have taken the approach of going for a minimum viable proposal. They hope that the proposal is the right size, big enough to be really useful, small enough that they can get it right, and open to extensions that will fill out the reflection functionality at a later time. This minimal viable proposal is one where introspection is nearly complete, but code injection support is minimal. Focusing on introspection first makes sense for two reasons. First, the complications of code injection are harder to solve than the complications of introspection. Second, code injection without introspection is mostly useless, but introspection without code injection is very useful. This proposal is entirely compile time. P2996 is making its way through the standards committee on both the language and library tracks. The basic design has been approved by both the language evolution and library evolution groups, though some tweaks to the design will be discussed in the standards committee meeting next week, where the proposal will start being reviewed by the core and library wording groups. If none of that made any sense to you, because you are not familiar with the inner workings of the C++ standards committee, don't worry. The TLDR is that reflection is on track to make it into C++ 26. It's not certain. There is still plenty of work to do, but the chances are good. On to the actual contents of the proposal. All reflection values have the type std meta info. Different reflection values are different compile time values of the meta info, not different types. Meta info is an opaque scalar type that is only useful at compile time. All functions that work with meta info objects are const-eval, which means they are compile time only. Why one type for all reflection values rather than different types for different kinds of things like in C#? Two reasons. First, the C++ language has changed in the past and it will continue to change in the future. Reflection needs to represent the structure of the core language. Reacting to language changes will be easier if the structure of the language is not encoded in its type system. Second, and I think more importantly, it is easier to represent a heterogeneous container or a collection of mixed things. A list of template arguments can be stored in a vector of info, even if those template arguments are a mix of type template arguments, non-type template arguments, and template arguments. The reflection operator, which is how you transition from the code world to the reflection world, is a prefix unary double caret operator. The operand can be a type or the global namespace or almost anything with a name. The result of the double caret operator is always a compile time value of type std meta info, and is the reflection of the operand. So if we take the reflection, if we apply the reflection operator to int, we get a reflection of the built-in type int. If we apply the operator to std vector of int, we get a reflection of the type std vector of int and allocator of int. Just remember, vector has a default parameter, which shows up in the reflection. If we take the reflection of just a vector without any arguments, that's a reflection of the class template std vector itself. It's not a reflection of any particular instantiation of it. This is the reflection of the type alias std string. If you remember, std string is an alias for basic string of car and the other default parameters. So type aliases can be reflected separately from the types that they represent, which is important when dealing with type alias templates, which can have their own set of parameters and their own information about them. And there is, of course, a way to get from the alias to the type underneath. This is a reflection of the global namespace. This is a reflection of the namespace std chrono. The global namespace is unique because it doesn't have a name, so a new syntax for getting the reflection of that. And finally, this is the reflection of the function std fopen. The reflection operator was originally proposed as a single caret rather than a double caret, but pushback from the implementers of Clang, where the single caret is ambiguous with an operator in Objective-C, led the reflection proposal authors to change to the double caret. There is still some resistance to the double caret, and some people prefer using a keyword rather than punctuation, so the spelling of the reflection operator could, in theory, change again. This will be discussed in the Standards Committee meeting next week, where hopefully some decisions will be made. For this presentation, I'm assuming that the reflection operator will be a double caret. And if a new syntax is chosen, the semantics should remain the same. This is a syntax-only discussion. To go from the reflection world to the code world, use a splicer, which is a pair of brackets made up of square brackets and colons. The operand inside the brackets must be a compile time expression that is, or that can be implicitly converted to, std meta info. Splicers are hard to describe and are best understood with examples. Here we get the reflection of the built-in type int and store it in the constexpr variable r. Then we splice the reflection variable r back into the code world. Because r is the reflection of int, variable x has type int. It's possible to get the reflection of something and immediately splice it back into the code. It is legal, but not particularly useful. You may have noticed the use of type name before each of the splices. The keywords type name and template are sometimes required before a splice operation, similar to how type name and template are required before names that depend on a template parameter. In all these cases, the keywords help the compiler with its syntax parsing. In the example with the template keyword in this slide, the compiler needs to know that the splice of VT is a template so that it knows how to correctly parse the less than character just after the splice. A splice can be used almost anywhere that the reflected thing is valid. So if we have a reflection of a type, such as long, we can use that anywhere that we could use a type, like the argument, like one template argument to std vector, or the type of a variable, or the type inside a static cast. Note that the type name is not needed in the static cast because syntactically only a type can appear there. If we take the reflection of a namespace, we can use that, we can splice that back into the qualifier part of a qualified name. A reflection of a function can be used when taking the address of that function or when calling the function. And the reflection of a non-static data member of a class can be used on the right side of a dot, of the dot operator, to indicate that field within the class. But note that this is a reflection of the Z within class A, not just any field that's called Z. So if we have two classes, each with a data member named Z, when we take the reflection of the Z within class A, we cannot splice that into a member expression of an object of type B. The compiler will report an error as shown here. Next, we'll discuss the meta functions in the proposal. They are all const-eval functions in the std meta namespace. The parameters are generally reflection values of type std meta info. The return type is appropriate for whatever was asked, which is often a Boolean, a meta info, or a vector of meta info. I won't go over all the meta functions because there are too many, but I will cover different groups of meta functions so you can get a good sense of what they can do. So these are the ones that you can use to find out what type of info object you have, what kind of thing it is reflecting. Since info is used for a reflection of anything, you need ways to figure out what it actually is. So it can be a namespace function variable, on, and be all these things and a bunch more. So you have all these functions to ask, what is this thing? There are meta functions for asking about the name of a thing. Identifier of will return the simple name of a thing, either as a basic string or as a UTF-8 encoded string. If the thing doesn't have a name, which can be the case for, among many other things, class types and for some non-static data members, then calling identifier of is a compilation error. That's why there is a function named hasIdentifier to query whether or not a thing has a name. There are meta functions to get the display name of the thing, either as a basic string or as a UTF-8 encoded string. The contents of the display name are implementation defined, but should hopefully be something that lets humans uniquely identify the thing the reflection represents. While overloaded operators sort of have names, their names are not identifiers. So identifier of doesn't work well. Instead, there is an operator of function that returns an enumeration indicating what operator is being overloaded. You can ask for the source location of a thing. The implementation is supposed to return the location of the thing's definition or of one of its declarations if it doesn't have a definition. All of the queries that can be done with type traits can also be done with reflection meta functions. To avoid naming conflicts, for every type trait whose name starts with is, the corresponding reflection meta function has type appended to the name. So type trait stood is function becomes reflection meta function. Stood meta is function type, which indicates whether or not the meta info is the reflection of a function type. And it's done this way so it doesn't clash with stood meta is function from several slides back that is used to query whether or not the meta info is the reflection of a function. Or the function and its type are different things. There's all sorts of meta functions for querying about things that you can't do with type traits. Like you can find its accessibility. Is it public, protected, or private? What kind of linkage does it have? Is it virtual or is it an override? You can ask things about, it's about member functions. Or other things. Is this function defaulted or is it declared as deleted? Or if it's a constructor, is it explicit? And some of the most used meta functions are for getting the members of things. You can call members of on a class or a namespace, and it will return all the members. The other bases of, static data members of, non-static members of, you can call on classes to get the things they described. You can get the list of enumerators in an enumeration with enumerators of. Now when called on classes, this returns all the members as appropriate regardless of accessibility. So there's a big interest in getting just the public things. So there are versions of these functions for classes that will get just the public ones. Some of the ones that I find most interesting are about templates. You can ask, is this a template specialization with has template arguments? Right, is it a specialization of something? It could be a specialization of a function or a class or a type alias or a concept. And if so, you can get the underlying template, and you can also get the template arguments that were used to create that specialization. The reflection operator cannot be applied to expressions, really only to types and to names. But you can still get a reflection of compile time values of structural types. But you have to go through a different interface. So you have to call reflect value. You give it any compile time value of a structural type, and it returns the reflection of that. There's also reflect object and reflect function. Reflect value and reflect object seems kind of similar, but the differences of them are important, so I won't go here. And then if you have a reflection of a value, you can get that value back into the code by calling extract. You give it a reflection. You give it the reflection and the type that you know that reflection to be, and it will give you back a compile time value that was reflected. So a lot of these functions take a reflection of a certain kind. What happens if you pass one of the wrong kind? For queries that return a Boolean, it returns false if the argument is nonsensical. So if we ask if the type int is a pure virtual function, it's just going to return false because it is not a pure virtual function. But if it's not a Boolean query, if it's asking for something else, then the usual behavior is that compilation fails. So if we try to ask for the offset of int, that doesn't make sense because offset of expects a non-static data member. There's no value that it can give that would make sense, so it fails to compile. And the compiler tells us why. So it expected a non-static data member, but we gave it a type. There are some more features in the reflection proposal still to be covered, but we've covered enough that it's time for some real examples. But before doing that, we need to take a short detour. For compile time reflection to be really useful, there must be a way to loop over a collection of a collection at compile time. And no, a regular for loop inside a constexpr function isn't good enough. There is a standards proposal to add constexpr loops to the language, referring to them as expansion statements. That proposal stalled for a while, but it is moving again. Even though expansion statements aren't in the standard yet, it is so useful to reflection that P2996 and the slides in this presentation are written assuming that expansion statements exist. When you see what looks like a range-based for loop with template in front of it, read that as a loop that is expanded and unrolled at compile time. Most compilers don't implement expansion statements yet, so a workaround is available. The syntax is rather ugly, but the effect is similar. The template for syntax will be used on these slides, but the expand syntax will be used in all the compiler explorer links so that the code will actually compile. One final look at our size length problem. If the argument is of a class type, get all the members of that type and iterate over them. If the member is a function, named, size, or length, that can be called with no arguments and returns an integer, then call that member function. Note how reflection and requires expressions play nicely together here. Reflection makes it easy to look through all the member functions, searching for ones that fit whatever criteria we are looking for. But it is much easier to use requires expressions to validate that whatever is found can be used in the way that we want to use it. Now back to the very beginning of this talk, where I hopefully piqued your interest with the magical parse options function. This is how the magic works. The type that holds all the configuration options is passed as an explicit template parameter. Iterate over all the non-static data members of that class. Search through all the command line arguments, looking for one that matches the name of the non-static data member with a double dash in front. If the parameter is of type bool, that's easy to process. Otherwise, we use I/O streams to parse the value of that argument. Throw in a little bit of error checking, and we have a decent generic command line parser. There are a few functions in P2996 that are worth calling out because they are not like the others. Splicers behave as if they insert the thing being reflected directly into the source code, and then the compiler compiles the code as if the thing being reflected had always been there. But the functions substitute and define aggregate change the state of the compiler without injecting any code that is then compiled. The function substitute performs a template substitution. The inputs are the reflection of a template and a range of the reflections of all the template arguments. The output is the reflection of the type that was created. The substitute function combines the template and the template arguments into a type, kind of like the line at the bottom, except that you can't do it that way because args is not a pack that can be expanded. If the template arguments that you pass to substitute don't match the template parameters of the given template, that's a compiler error. Sphene or substitution failure is not an error does not apply here. When you are not certain that the template arguments you have will work and you need to handle that situation gracefully, then you can call can substitute first to check if the call to substitute would succeed. This example attempts to automatically propagate an allocator from the container to the elements owned by the container. If a container has a non-default allocator and the value of the container is allocator aware, we can automatically change the value type to use the custom allocator. I don't know if this is actually a good idea, but until now, it hasn't been possible, so we couldn't even explore the issue. Reflection now makes this possible, so we can now figure out if automatic allocator propagation is useful in some situations. This is how we can change the allocator of an allocator-aware type. If the given allocator is the default system allocator, or if the value type doesn't have any template arguments, then there is nothing to do and we bail out early. If the arguments pass those checks, then iterate over the template arguments of the value type that was given to the container. If the template argument is a specialization of stood allocator, replace it with a specialization of the desired allocator. The allocator traits rebind is necessary because the template arguments for the two instances of the allocator are different. Once the necessary adjustments to the template arguments have been made, the new value type is created by calling substitute. And this is how change allocator would be used. In the definition of the container, we set the value type to the result of calling change allocator. If the value type is not a template specialization, or if none of the template arguments of the value type look like an allocator, then change allocator doesn't do anything. The value type of the container is the value type that was specified. But when the value type has an allocator as a template argument, then change allocator may change the allocator. Note that stood vector has a default template parameter for an allocator. So when we say vector event, the compiler sees vector event with allocator event. In this case, change allocator returns a different type, a vector event with custom alloc event. While substitute will create template substitutions out of reflection values, define aggregate will, as its name implies, define an aggregate class type using only reflection values. It doesn't create the class entirely out of thin air. One of the inputs is the reflection of an incomplete class, which must have already been declared. For now, only non-static data members are supported because they have the best combination of being both useful and easy to implement. Other kinds of members may happen later. In earlier versions of the proposal, this function was named define class. The name was changed to define aggregate recently because aggregate is a better description of the type that is defined. The data members that define aggregate should create are specified with the reflection of the type of the data member and a struct containing other settings. Only the type is required. Everything else, including the name, is optional. Name type is a type that can be created with any compile time string-like thing, including a string literal, a stood string, or a stood string view, in either regular or UTF-8 encoding. The function data member spec is used to create the reflection of the data member that define aggregate needs. Here's a simple example. The code at the top behaves the same as the code at the bottom. Note that calling define aggregate with a template specialization that hasn't been fully instantiated yet behaves the same as an explicit specialization of the class template. Here's an example that could be very useful to developers in the high-performance space. Even though an array of structs is more readable and more maintainable, a struct of arrays often has better performance due to increased vectorization and caching effects. In many applications, data structures will be manually changed to use struct of arrays, even with its higher development costs and maintenance costs. Well, now with reflection, that change doesn't have to be done manually. Given any struct whose data members are scalar types, a new struct with corresponding members that are arrays instead of scalars can be automatically created. To do that, iterate over the data members of the given type. Create a new data member that has the same name as the old data member, but whose type is a stood array of the old type and the desired size. Use define aggregate to define a new type with the new data members. The implementation may look a little complicated, but the use of this is simple, and that's one of the goals of software engineering, to make things easier for the end user. It would be even nicer if the struct of array class came with member functions that made it look like an array of structs. but that will have to wait until define aggregate or some other related meta function can define member functions and not just data members. You may say that this all looks good, but even if it makes it into C++26, it will be at least several years before I can try it out. Wrong. There are already 2.5 implementations available on Compiler Explorer. But be warned that all these implementations are preliminary. They have plenty of bugs and unimplemented features. So please don't use reflection in production code just yet. But please do try this out and play with it and give feedback to the paper authors. So EDG, Edison Design Group, they license out a C++ front end to other companies to use. They have implemented reflection behind a hidden option, but they have made that implementation available on Compiler Explorer. So choose EDG, Experimental Reflection, and you can try all this stuff out. People at Bloomberg have implemented reflection in a fork of Clang, made it available on Compiler Explorer. You should select Clang, Experimental P2996 as your compiler. You'll probably want to add the freflection new syntax option when compiling, and the GitHub repo at Bloomberg at the URL there has more details and more what other options are available when compiling. Then the NVIDIA HPC C++ compiler, the one that I work on, has an EDG front end. So we've taken the implementation that EDG has, and in our compiler, behind a hidden option for reflection, that compiler is available on Compiler Explorer. So you can try it out there, but you need to use these two options to get it, to get the reflection behavior. And this is the release compiler, so you can download it and try it out on Linux. If you have a bigger application where you want to try out reflection, you can do it this way. Application that's too big to put up on Compiler Explorer, you could try it out this way. But be warned, our implementation is lagging a little bit behind. We don't get all the updates as EDG makes them right away. So this has a somewhat older version of the reflection implementation. I have one more example on how reflection can solve real-world coding problems, automatic serialization. There are some very good serialization libraries out there. They have powerful features and can handle most things automatically. But one important feature can't be done automatically. Serialization frameworks don't know what to do with classes. In existing libraries, there is no practical way to peer inside a class to see what needs to be serialized. So users are required to supply a function that tells the library how to serialize a class. The introductory tutorial for Boost serialization contains this example. To use class GPS position with Boost serialization, the user needs to write a function named serialize with the right signature. This big hole in automatic serialization can be filled by reflection. The serialization code can use reflection to look at all the class members and make reasonable decisions about how to serialize them. To demonstrate this point, I wrote a very small and basic serialization class. The goal of this is to show how reflection can be useful. It is not meant to be a top-notch serialization library. There's a lot of boilerplate code to handle non-class types. This is the serialization code. The deserialization looks a lot like it. Now for the interesting part. This is the code to automatically serialize a class or struct. Iterate over all the base classes, serialize each one. Then iterate over all the data members and serialize each one, using a splice of the reflection of the data member to access it by name. When I started on this serialization example, I was expecting there to be more reflection-related code. I was pleasantly surprised, however, by how powerful reflection is and how easy it is to do things that used to be impossible. The code to deserialize a class or a struct is very similar, except that bit fields complicate things a little bit. It's not possible to take the address of a bit field or create an L-value reference to a bit field. So we have to deserialize into a regular variable and then assign that to the bit field. Reflection can automatically deal with many user-defined classes, but not all of them. References and other non-assignable members won't work because deserialization has no way to set those members. Unions can't be serialized automatically because the code doesn't know which member of the union is currently active. Pointers are problematic because it's difficult to set the pointer correctly during deserialization. So the main conclusion is that a good serialization framework must allow the user to control how a class is serialized, even if most classes can be handled automatically. There's enough confidence in the success of P2996 that some proposals are already being built on top of it. I'll briefly mention some of them here. None of these, except maybe the reflection of function parameters, are likely to make it into C++26. And some of them may never happen at all or may look very different when they make it into the language. But I think it's worth seeing what people are working on right now. So in P2996, you can't take the reflection of function parameters because the names are not consistent. All these declarations in one definition of distance can appear in the same file, even though the names of the parameters are completely different. So what should identifier of return for these parameters? That's not an easy question to answer. So that's been pushed off into a whole separate paper. So P3096 works on this. And their current proposal is that to use identifier of, the parameter names must be consistent across all the declarations of a function. Now, if you don't care about consistent thing, you can use the new function anyIdentifier of, which will pick one of the names. If the names are inconsistent, it will just pick one. So this proposal will be discussed next week. I don't know what the outcome will be. I don't know yet what people will think of the requirement of having consistent names. So we'll see. The next proposal to look at is token sequences. A token sequence is what its name implies, a sequence of arbitrary C++ tokens. The only requirement is that curly braces need to be balanced. As with everything reflection related, the type of a token sequence is a std meta info. The tokens in a sequence don't have to be syntactically or semantically valid, they just have to be tokens. To be of any use, in the end, you need tokens that are both syntactically and semantically valid, but the intermediate token sequences don't need to be meaningful by themselves. Token sequences are only useful if we can inject them back into the code so the compiler will parse them and compile them. This is done with the functions quinjection and namespace inject. Creating and injecting token sequences that consist entirely of fixed tokens is not useful. To accomplish anything, there needs to be a way for token streams to contain variables or placeholders of some sort that are filled in with the token sequences injected. Token sequence proposal has three ways to do that: a compile time value, an identifier, or a token sequence. Two quick examples. This is roughly how enable if is currently implemented, but this can be confusing to those unfamiliar with template metaprogramming. The name enable if implies that there should be an if in there somewhere, but there is none to be seen. When token sequences are used instead, the implementation of enable if is much more clear. There's a very obvious if statement, and it's easy to figure out that type is defined when the condition is true and not defined when the condition is false. Std tuple is a very useful class, but it's annoyingly hard to implement. In particular, it's really hard to define the data members of a tuple because there is no good way in C++ to turn a list of types into a sequence of declarations. Existing tuple implementations rely on recursive template-based classes to do that. But with token sequences, defining the data members of the tuple is almost trivial. Iterate over the type list within a const-eval block, creating a token sequence defining a data member with a manufactured name and the correct type. That's it. Defining all the member functions and free functions for std tuple is left as an exercise for the reader. So in P2996, you can't reflect templates, or you can get the reflection of a template, but you can't reflect anything else about it. You can only sort of pass it to substitute. That's because the members of templates are abstract. They're not resolved to something that you can really reflect until the template is instantiated. So how do you reflect something inside the template that may be dependent on template parameters? A proposal says, let's use token sequences. So all the meta function queries on things inside a template, they return a token sequence rather than the other reflections that were useful. And you can then use those tokens, inject them back in to create a new template, to define a new template. So this is useful if you have one template and you want to create another template that's similar. You can extract the token sequences that you want from the first template and use them when constructing your second template. So here's a tiny example. Class template C has two base classes, one of which depends on a template parameter. When we use template bases of to get the reflection of the first base class, it returns a token sequence with the tokens public, double colon, and B1. The reflection of the second base class is also a token stream. Note that the non-dependent names are fully qualified and the names of the template parameters are canonicalized. See the paper for why. The keyword public needs to be in the token sequence because there is no other way to indicate the accessibility of the base. So one last thought about future directions. If you really want to see the future of reflection and get a glimpse of where it might be headed, go back in time 7 years and watch Herb Sutter's CPPCon keynote about metaclasses. The details have changed a lot since then, and Herb has recently revised his paper to be based on the latest reflection and token sequence proposals. But the idea of taking code injection to the extreme is still worth considering and pursuing. So if you like watching conference talks, I'll recommend Welcome to the Metaverse by Inbal Levy from ACCU this year, or Reflection-Based Libraries to Look Forward to from CPPCon, and then the closing keynote at CPPCon, Gazing Beyond Reflection for C++ 26 by David van der Voorde, who is the lead author or one of the lead authors of the reflection proposal and the person who's implemented it at EDG. That's a good look from the inside, from someone on the inside of what he thinks about reflection and where it's going. If you're familiar with how standards committees work and like seeing how the sausage gets made, here's a list of papers related to reflection that you might find interesting. But if large, inefficient, contentious committees are not your thing, that's perfectly fine. You can safely ignore this slide. What I hope you will take away from this presentation. C++ reflection is coming. There is a very good chance that it will be in C++ 26, but even if it misses that, it will be in the standard before too long. C++ reflection happens at compile time. If you want to use reflection, you should up your compile time programming game. But you don't need to master template metaprogramming, since reflection is based on non-template const-eval functions. C++ reflection is best at reducing the amount of boilerplate code, making it possible to do generically what currently has to be done manually. There is still lots of work to do. If you are interested in reflection, please try it out, connect with others who are also interested in reflection, give your opinions and suggestions, and pitch in however you can be most useful. Thank you. Right behind you.
Thanks for the talk. Can you reflect on overload sets?
The question was, can you reflect on overload sets? Currently, no. That's being discussed. That's complicated to do. So that won't be. That's not in the initial proposal, but yes, that is being discussed and worked on.
So that was going to be my question, but I also think that there is a way you can do it, because can't you just reflect on the global namespace and then search through it for
you can search through a namespace and find the things that you can find all the overloads that you're doing, but you can't have the compiler go look up the name and find all the potential overloads and reflect on that.
for the reflection on templates, is it just going to give you the body of the primary? What if there's a specialization?
There's discussion on that, which I didn't read in detail. I think you would get a reflection of the partial specialization separately from the
that's
reflection
good,
of the main
yeah.
template, and then you would ask questions about that partial specialization.
Okay. How would you get the partials?
That's discussed in the paper. I don't know.
Okay.
Hi, since you mentioned C# and serialization, I was wondering, can you reflect on attributes? And is there any plan for custom attributes in C++? Because in C# it's very powerful together, like for serialization, for example. You can define serializers and such.
Okay. Gazing beyond reflection for C++ 26 from the CPPCon keynote. The last part of that talk is about reflection of attributes, or as he calls them, annotations. So there's a new proposal out there. It's not on that list. Oops, I missed that list. To actually create he calls them annotations. So they look like attributes, but they're a little bit different, so the compiler cannot ignore them, and then you can reflect on them in the code. So you could use these, if these annotations make it, you could use these annotations in your command line option parsing example. So you can annotate the fields in your struct to tell the parser how to react with them. So yes, there is work going forward on, it's not in the initial proposal, but there is work going on reflection of attributes or annotations or something like that.
For the preprocessor, there's the option to show you the source code after the dust has settled. Is there something similar for reflection? That to see the code as if it was written manually?
No, the same way that there's not really any option to show you the templates after they've been instantiated or how your context per functions are being evaluated. So C++ in general has a big hole there in debugging and seeing what the compiler does behind the scenes, and reflection probably just makes that worse.
Can I ask one more question?
Yeah.
Can you, so in what's the step that happens before reflection and the one that happens after reflection? Template instantiation comes later, right? Or is it all mixed together?
Well, if your reflection operator and splicers are inside a template, then those are evaluated as the template is instantiated. So yes, they are processed as the code is being processed, which means, yeah, and if it's in a template, it's as that template is being instantiated. Okay, and think we are out of time?
We are out of time, so.
Okay.
I guess everyone has to come to
Yeah.
and ask the questions manually.
Okay. Thank you all.